The most dangerous thing aboard a real starship would not be radiation, collision, or mechanical failure. It would be time itself. Given enough of it, medicines decay, precision disappears, knowledge dies, and one microscopic defect can turn humanity's greatest machine into a civilization-sized tomb. Tonight, every hidden countdown will be exposed to discover how long a real starship could truly survive alone in deep space. Get ready. The journey begins now. A dead starship does not stop. It keeps moving through space, same direction, same velocity. It may continue for millions of years. The first thing it loses is not motion. It is the ability to recover from the next mistake. Voyager 1 has been operating for nearly half a century. Launched in 1977, it is still sending signals toward Earth from beyond the heliosphere. It travels at roughly 17 kilometers per second relative to the Sun and remains the most distant human-made object in existence. By November 2026, Voyager 1 will be almost one light day from Earth. That distance changes the meaning of communication. A command transmitted from Earth will need nearly 24 hours to reach the spacecraft. If Voyager responds immediately, the confirmation will require nearly another day to return. One question. One answer. Almost 2 days. Voyager is an extraordinary demonstration of mechanical endurance. Yet it is also an easy machine to misunderstand. Its surviving radioisotope thermoelectric generators now produce only a few hundred watts of electrical power. That is comparable to the demand of a handful of household light bulbs. The available output continues to decline as the plutonium-238 fuel decays, and the thermocouples that convert heat into electricity slowly degrade. Engineers have responded by shutting down instruments and heaters. They are not keeping the entire spacecraft young. They are carefully deciding which parts are allowed to die so that a few essential functions can live longer. Voyager carries no crew, no atmosphere, no drinking water, no crops, no surgical equipment. It does not need to maintain pressure, remove carbon dioxide, sterilize waste, manufacture replacement valves, or protect children from radiation. A real starship would need to do all of those things at once. It would contain a power station, a water treatment network, an atmospheric processing plant, a farm, a hospital, a machine shop, and a navigation center. If the voyage lasted longer than one human lifetime, it would also contain a school, a government, and a population that had never seen Earth. Voyager is not a small version of that machine. It belongs to a different category of survival. Voyager crossed the heliopause in 2012. The heliopause is the boundary where the outward pressure of the solar wind gives way to the plasma environment between the stars. Crossing it made Voyager the first spacecraft to operate in interstellar space. But it did not fully leave the solar system in every physical sense. Far beyond Voyager lies the Oort cloud, a vast, distant population of icy bodies still gravitationally bound to the Sun. NASA estimates that Voyager may require centuries to reach its inner edge and tens of thousands of years to travel beyond the cloud. That distinction matters. Interstellar space does not begin with a clean line painted across the darkness. The influence of the Sun fades in layers. Its useful light weakens. Its magnetic protection changes. Communication becomes slower. Support becomes less practical. Eventually, every connection to Earth becomes a memory. The International Space Station reveals the other side of the problem. It has supported continuous human presence since November 2000. It is one of the most complex machines ever assembled outside Earth. But the station is not independent. Cargo vehicles regularly bring food, clothing, scientific equipment, water, gases, and replacement hardware. Ground controllers monitor its systems. Engineers study anomalies and develop procedures. Crew members rotate back to Earth, where hospitals, laboratories, and entire industries remain available. The station can lose a pump and receive another one. It can discover a software problem and receive a patch. A sick astronaut can, under the right conditions, return to a planet with specialist physicians and advanced medical equipment. And all of this support exists while the station orbits only about 400 kilometers above Earth. A Starship would have none of it. There would be no warehouse behind it, no emergency launch, no replacement crew, no technician on Earth able to reach inside the machinery. Even advice from home would become old before it arrived. NASA's CHAPIA, one experiment, showed how difficult a far smaller step can be. 4 people spent 378 days inside a 1,700 square foot simulated Martian habitat. They experienced isolation, restricted resources, equipment problems, and delayed communication. It was a serious test of human health and performance. Yet, 378 days is still only a little over 1 year. An idealized journey to Alpha Centauri at 10% of light speed would last roughly 42 years before acceleration and deceleration were fully considered. CHAPIA 1 would have to be repeated more than 40 times without resetting the habitat, replacing the infrastructure, or bringing the crew home. That exposes 3 different meanings of survival. The first is ballistic persistence. An object remains on its trajectory because space provides little resistance. Its engines may be dead. Its computers may be silent. It still moves. The second is functional survival. Some systems continue performing their assigned tasks. The spacecraft generates power, processes data, or transmits a signal. Voyager exists at this level, although its remaining capability is being carefully reduced as its power declines. The third is recoverable survival. A system fails, but the spacecraft can diagnose the fault, isolate the damage, and restore the lost function. It has enough energy, tools, materials, knowledge, and healthy personnel to recover. Only at this third level is a crewed Starship truly alive. This creates what engineers might call a mission reliability envelope. Inside that envelope, failures remain manageable. Electrical power is sufficient. Replacement materials are available. The crew has the expertise and time to perform repairs. Backup systems can carry the load while damaged equipment is restored. But the envelope can shrink, fuel is consumed, spare parts disappear, sensors drift, tools wear out, radiation damages electronics, crew members age. A repair that once required 3 hours may require 3 days because access panels are warped and documentation no longer matches the modified machinery. Nothing has to explode. The ship may look healthy while its ability to recover is quietly vanishing. That is the hidden clock aboard every interstellar vessel. It does not measure how long the reactor can run or how many years remain before arrival. It measures the distance between the ship's current condition and the first failure it can no longer reverse. A Starship does not necessarily die on the day its first critical system fails. It may die years earlier, on the day the last tool needed to repair that system becomes unusable, or when the final compatible spare is consumed, or when the only person who fully understands the machinery is no longer able to teach a successor. The failure simply has not happened yet, and the first clock may not be buried inside the engine. It may already be ticking in every breath, where a change of only a few millimeters of mercury in carbon dioxide partial pressure could determine whether the crew remains clear-minded enough to save the ship. The air inside the ship still looks clean. There is no smoke, no strange color, no smell that suggests danger. Yet the crew has begun to change. One engineer reports a headache after waking. Another struggles to sleep through the night. Reactions become slightly slower. Small disagreements last longer. 2 technicians examine the same stream of environmental data and reach opposite conclusions. The life support display remains green. According to the ship, nothing is wrong. That is what makes atmospheric failure so dangerous. A fire announces itself. A hull breach produces a pressure alarm. Rising carbon dioxide may arrive quietly, hidden inside air that still looks perfectly breathable. A resting human body continuously consumes oxygen and produces carbon dioxide through cellular metabolism. The carbon in food is oxidized as cells extract usable energy from carbohydrates, fats, and proteins. Carbon dioxide enters the blood, travels to the lungs, and leaves the body with every exhalation. Water vapor leaves with it. Inside an open environment, those waste products disperse into an enormous atmosphere. Inside a sealed spacecraft, they remain part of the cabin unless machines remove them. Every breath changes the chemistry of the ship. On the International Space Station, one of the systems responsible for reversing that change is the Carbon Dioxide Removal Assembly, or CDRA. Cabin air passes through a 4-bed molecular sieve containing zeolite crystals. Zeolites are porous minerals built from silicon, aluminum, and oxygen. Their microscopic cavities can selectively adsorb molecules under controlled conditions. In the CDRA, one section first removes water vapor. The dried air then reaches another bed that captures carbon dioxide. The system operates cyclically. While one side adsorbs carbon dioxide from cabin air, another is regenerated by heating and exposure to vacuum. The trapped gas is released, and the bed becomes available for another cycle. By alternating between beds, the assembly can remove carbon dioxide continuously. NASA reports that a CDRA operating with both carbon dioxide removal beds can support approximately 6 human equivalent units. Its operational design is associated with cabin carbon dioxide partial pressures in a range of roughly 2.0 to 3.9 millimeters of mercury. That unit matters. Carbon dioxide risk is not described only by its percentage of the atmosphere. Engineers and physicians often examine its partial pressure, the share of the total atmospheric pressure produced by carbon dioxide molecules. The cabin can maintain apparently normal total pressure, while the composition inside that pressure slowly changes. Nitrogen may still be present. Oxygen may remain near its target. Nothing has to trigger a dramatic decompression alarm, but carbon dioxide can still rise. Once inhaled, it reaches the alveoli, the microscopic air sacs where gases move between lungs and blood. Carbon dioxide crosses the thin alveolar membrane according to pressure gradients. If the inhaled level rises, the body becomes less able to release the carbon dioxide carried back from its tissues. More remains dissolved in the blood. Some reacts with water and shifts the body's acid-base balance. The respiratory system responds by increasing ventilation. Blood vessels in the brain dilate. This cerebral vasodilation can contribute to pressure sensations and headaches. The nervous system notices the change before the air appears dangerous. NASA has reported that the probability of astronauts reporting headaches increased from roughly 1% to around 4% as the 24-hour average carbon dioxide partial pressure rose from approximately 2.5 to 4 millimeters of mercury. That does not prove that every astronaut will suffer cognitive impairment at those levels. Research into memory, concentration, decision-making, and task performance at spacecraft-relevant carbon dioxide concentrations has produced mixed results. Some controlled studies have found no measurable decline in astronaut-like subjects at concentrations comparable to spacecraft cabins. The scientific uncertainty is important. It means a crew cannot assume that a headache proves carbon dioxide is responsible, but it also cannot assume that a technically acceptable reading guarantees every person will remain unaffected. Individual sensitivity varies. Exercise increases metabolic production. Sleep compartments can develop local pockets of carbon dioxide if air circulation is poor. A sensor mounted in the main cabin may report a safe average, while a crew member's breathing zone experiences something different. A spacecraft does not contain one perfectly mixed parcel of air. It contains ducts, corners, sleeping stations, equipment bays, and temporary obstructions. Fans must keep the atmosphere moving. If circulation slows, carbon dioxide can accumulate near faces, behind panels, or inside enclosed work areas. Removal is only half of the atmospheric equation. The crew also needs oxygen. On current spacecraft, oxygen can be produced through water electrolysis. Electrical energy splits water into oxygen and hydrogen. The oxygen enters the cabin atmosphere. The hydrogen becomes a chemical resource that can help recover water from carbon dioxide. That recovery occurs inside a Sabatier reactor. Carbon dioxide collected from the cabin is combined with hydrogen over a catalyst. The reaction produces water and methane. The water can return to processing, where it may once again provide drinking water or feed the oxygen generation system. This creates an elegant loop. Human metabolism produces carbon dioxide. Machinery captures it. Electrolysis produces hydrogen. The Sabatier process turns part of those streams back into water. But the loop is not completely closed if methane is discarded. Methane contains carbon and hydrogen. If it is vented into space, those atoms leave the ship's usable inventory. Over a mission lasting months, resupply can compensate. Over decades, every persistent loss becomes part of a mass balance that cannot be ignored. And every machine in the loop has components that age. Zeolite beds can become contaminated, heaters can degrade, valves can stick, fans can lose efficiency, catalysts can be poisoned by trace compounds. Electrolysis cells can experience membrane deterioration and changes in electrical performance. Then there are the sensors. A carbon dioxide detector does not have to fail completely to become dangerous. Its response can drift as sensing surfaces age. Optical components become contaminated, or electronics accumulate radiation damage. A reading that is wrong by a small amount may still look believable. This is sensor drift. Normally, engineers control drift through calibration. A sensor is compared with a trusted reference, and its output is corrected. But an interstellar ship cannot return its instruments to a laboratory. Its reference equipment is trapped inside the same radiation environment, exposed to the same aging processes. Eventually, calibration itself can become uncertain. 3 sensors may produce 3 different readings. Majority voting appears to solve the problem, but only if their failures are independent. If all 3 were manufactured from the same materials, use the same software, and breathe through the same contaminated sampling line, they may drift in the same direction. That is a common cause failure. Redundancy protects against an isolated fault. It does not automatically protect against a shared weakness. True resilience requires functional diversity. One sensor might use infrared absorption. Another might rely on a different measurement principle. A third could infer atmospheric imbalance from independent flow and metabolic data. The same principle applies to carbon dioxide removal. 2 identical CDRA units provide capacity and backup. But if the same contaminant poisons both, duplication is not enough. Different mechanisms create stronger protection. The most dangerous sequence begins when several small degradations connect. Carbon dioxide rises. Some crew members develop headaches or disrupted sleep. Fatigue makes diagnosis slower. A technician misidentifies a valve problem and changes the wrong control setting. Airflow through the removal system falls. The remaining bed takes a heavier load and regenerates less effectively. Carbon dioxide rises again. This is a positive feedback loop. Each consequence strengthens the condition that produced it. The atmosphere does not have to kill the crew directly. It only has to weaken the people responsible for saving it. And even if the carbon dioxide is finally captured, another closed loop is already under pressure. Air can be filtered again and again. Water has nowhere else to come from. Any molecule that leaves the ship's recoverable inventory will never be returned by a cargo vehicle. The ship does not lose a tank of water. There is no dramatic rupture, no glittering cloud of ice crystals expanding into space, no alarm announcing that the entire reserve is gone. It loses a little at a time. Some water remains trapped in solid waste, some stays inside filters and discarded maintenance materials. A small amount escapes when an airlock is vented. More is lost through leaks, sampling, cleaning procedures, and components that cannot be drained completely before replacement. Each loss seems harmless. By the time the total becomes frightening, the water may have passed through human bodies and processing equipment millions of times. That distinction matters because a closed water system does not simply store water. It continuously moves water through different chemical and biological states. Clean drinking water becomes blood plasma. Sweat, urine, and exhaled vapor. It becomes cooking water and wash water. It enters plant tissue, nutrient solutions, and cooling loops. Then machines must separate it from everything collected along the way. On the International Space Station, the water recovery system has demonstrated an overall recovery rate of approximately 98% after the addition of the brine processor assembly. NASA estimates that each astronaut requires roughly 1 gallon of water per day for drinking, food preparation, and basic hygiene. Without recovery, a crew of 6 would require thousands of gallons every year. Transporting all of that water from Earth would be enormously expensive. For a Starship, continued resupply would be impossible. The recovery process begins in several places. Water vapor from breath and sweat enters the cabin air. Condensing heat exchangers remove moisture as part of humidity control. Urine is collected separately and processed. Hygiene water and other wastewater join the recoverable inventory where the system architecture allows. These streams do not contain only water. Urine carries salts, organic compounds, and metabolic waste. Humidity condensate can collect skin particles, microorganisms, cleaning chemicals, and volatile compounds released by plastics, electronics, and human activity. The system must recover the water without allowing those contaminants to follow it back into the drinking supply. On the ISS, urine processing produces a concentrated residual stream known as brine. Older recovery methods left a significant amount of water trapped inside that material. The brine processor assembly was introduced to recover more of it. The processor uses membrane-based technology and warm, dry air. Water evaporates from the concentrated brine, passes through a specially designed membrane, and enters the cabin atmosphere as humid air. The station's humidity control equipment then captures that moisture. The waste from one machine becomes the input of another. Recovered water still requires purification. It passes through multi-filtration beds containing materials selected to remove dissolved contaminants. A catalytic oxidizer then breaks down low molecular weight organic compounds that remain in the stream. Sensors examine the processed water. Electrical conductivity is one important measurement because dissolved ions allow water to conduct current. A conductivity reading outside the accepted range suggests that purification was incomplete. Water that fails the check can be routed back for additional processing instead of entering storage. But conductivity is not a perfect description of safety. Some organic contaminants do not produce a strong conductivity signal. Microbial contamination requires separate controls. Temperature, sensor aging, and deposits on the sensing surface can distort measurements. The system therefore depends on layers of treatment, monitoring, and operational judgment. No single filter or sensor guarantees that the water is safe. The figure of 98% can also be misunderstood. It does not mean that the ship loses 2% of its entire water inventory every time water completes one universal circuit. A spacecraft does not have one simple loop in which every molecule travels through every component at the same moment. The percentage describes recovery from processed water streams under specified operating conditions. Actual losses depend on how much water enters those streams, how much remains in waste, how efficiently each subsystem performs, and how much escapes through maintenance, leakage, or operations. Still, the remaining difference matters. On the ISS, water that cannot be recovered can eventually be replaced by cargo missions. On a Starship, the total supply at departure is the maximum inventory the vessel will ever possess. Unless water can be obtained at the destination, even a small persistent demand for replacement water becomes serious when multiplied across decades. And the recovery rate may not remain at its original value. Membranes foul, catalysts lose activity, pumps wear, seals leak, adsorption media becomes exhausted or contaminated. A system that achieves 98% under carefully maintained conditions may perform differently after years of radiation exposure. chemical cycling, and repeated repairs. Then biology enters the pipes. Any surface that remains wet and receives trace nutrients can become habitat. Bacteria and fungi attach to metal, polymer, membrane material, or sensor housings. Initial attachment may be weak, but some organisms begin producing extracellular polymeric substances. This material forms the structural matrix of a biofilm. It is not simply a layer of free-floating microbes. It is an organized community, held inside a mixture of polysaccharides, proteins, nucleic acids, and other biological material. The matrix traps nutrients. It retains moisture. It anchors cells to the surface. It can also slow the penetration of disinfectants, allowing organisms deeper in the biofilm to survive treatment that would kill isolated cells. Inside the film, conditions are not uniform. Oxygen concentration can vary across microscopic distances. Acidity can change. Nutrients can accumulate near the surface, while deeper layers enter slower metabolic states. These microenvironments matter because they create forms of biological behavior that a sample of the surrounding water may not reveal. The water can appear relatively clean, while a mature microbial community remains attached inside a pipe. As biofilm thickens, it reduces the effective flow area. Pumps must work harder to maintain circulation. Pressure changes across filters increase. Loose fragments can break away and travel downstream, spreading contamination to valves, membranes, and storage tanks. Biofilm can also promote microbiologically influenced corrosion. Some microorganisms alter local chemistry at the material surface. Their metabolism can produce acidic compounds, consume protective chemicals, or create differences in oxygen concentration. Those conditions may accelerate localized corrosion beneath the film. The pipe can look intact from the outside, while damage develops underneath a biological layer no one can see. NASA research reported in 2025 continued modeling bacterial and fungal growth associated with the ISS water processor assembly. That work reflects an active engineering problem. Biofilm is not an invented monster waiting for future starships. It is already part of the challenge of managing water in a spacecraft. Aboard an interstellar vessel, the response could create another cascade. Biofilm increases resistance to flow. The pump draws more power. Membranes foul more quickly. Water quality becomes less stable. The crew increases chemical disinfection or raises treatment intensity. That stronger treatment places additional stress on seals, membranes, and polymer tubing. Material degradation creates rougher surfaces where microorganisms can attach more easily. Eventually, a weakened joint begins to leak. The leak may be small, but the lost water is only one consequence. Reduced coolant inventory can force equipment to operate at lower power. Limited water for electrolysis can restrict oxygen production. Crop irrigation may be rationed. Hygiene standards may fall. Increasing infection risk. Medical sterilization becomes harder. Water may also be positioned around sleeping quarters or storm shelters, because hydrogen-rich material can help reduce exposure to some forms of particle radiation. If that water must be moved elsewhere, radiation protection changes as well. A single water failure can therefore strike drinking supply, thermal control, oxygen generation, agriculture, medicine, and shielding. The crew does not merely drink the water. The entire ship is built around it. But water has one advantage. If it remains inside the vessel, machinery can keep purifying and redistributing it. Food is different. Food must be created again and again. It must grow, remain nutritious, and produce another generation, and the Starship's farm will never be allowed a failed harvest. A white film appears around the roots. At first, it seems local. One tray of plants grows more slowly than the others. The leaves remain green, but their edges begin to curl. Sensors detect a small change in nutrient uptake. Nothing looks catastrophic. The harvest falls by only a few %. Then oxygen production begins to fluctuate. Carbon dioxide remains elevated for longer periods after the crew's active cycle. Several plants stop flowering. The reserve food lockers are opened for the first time in years. No one knows whether the farm will recover in 3 weeks or 3 months. On Earth, a failed harvest can be offset by food from another region. Crops can be replanted with seed from a different supplier. Contaminated soil can be abandoned. Fertilizer, pesticides, and replacement equipment can arrive from thousands of kilometers away. A starship has only one agricultural region. It is enclosed by metal walls. A person consuming 2,000 dietary calories per day requires approximately 730,000 calories per year. In nutritional language, the word calorie commonly refers to a kilocalorie, but the familiar figure remains useful for understanding the scale. For a community of 100 people over 50 years, the requirement exceeds 3.6 billion dietary calories. That total does not include food discarded during processing. It does not include spoilage. Emergency reserves, crop failures, or changes in population. Children, pregnant crew members, injured patients, and people performing heavy physical work will have different nutritional needs. The ship cannot simply load billions of calories before departure and forget about food. NASA's current prepackaged spaceflight foods have a stated shelf life of roughly 2 years. That limit is not based only on the moment when food becomes microbiologically unsafe. A meal may remain technically edible while its flavor, texture, and nutritional value deteriorate. Fats oxidize, pigments change, proteins undergo chemical reactions. Packaging materials age. Repeated temperature variations accelerate some forms of degradation. Micronutrients create an even harder problem. Vitamin C, vitamin K, folate, and thiamine can decline during processing and storage. These compounds support processes involving tissue repair, blood clotting, nervous system function, and cellular metabolism. A food supply can therefore contain enough energy to prevent immediate starvation while becoming progressively less capable of maintaining long-term health. NASA's bionutrients research has examined ways to produce essential nutrients on demand using engineered microorganisms. The reason is direct. The existing stored food system cannot support missions extending far beyond approximately 2 years without additional strategies for preserving or replacing nutrients. For an interstellar voyage, agriculture is not an optional source of fresh vegetables. It becomes part of the life support machinery. A bioregenerative life support system attempts to use living organisms to recycle material in ways that physical and chemical machines alone cannot fully achieve. Plants absorb carbon dioxide during photosynthesis. Using light energy, they incorporate carbon into organic molecules and release oxygen. Their roots absorb nitrogen, phosphorus, potassium, and trace elements. Those nutrients support proteins, genetic material, membranes, energy transfer, and the regulation of cellular processes. The crew eats the edible biomass, leaves, stems, roots, and processing waste that are not consumed. Returned to the recycling system, microorganisms break complex organic material into simpler compounds. Nitrogen-containing waste must be converted into forms that plants can use without allowing toxic intermediates to accumulate. Water passes through the root zone, carrying dissolved nutrients. It is collected, treated, and recirculated. In principle, the outputs of one organism become the inputs of another. The European Space Agency's MELISSA program explores this type of closed-loop architecture. MELISSA stands for Microecological Life Support System Alternative. It divides the artificial ecosystem into compartments so that individual biological and chemical processes can be monitored and controlled. One compartment processes organic waste. Microbial communities break complex material into smaller compounds. Other bacteria transform nitrogen through controlled biological pathways. Additional compartments use photosynthetic organisms, including microalgae and higher plants, to produce oxygen and edible biomass. Bioreactors, membranes, filtration, and wet oxidation help move matter between these stages. The compartment approach makes a biological loop more predictable than a single uncontrolled ecosystem. If one process becomes unstable, engineers may be able to isolate it before the disturbance spreads. But Melissa is a research platform, not proof that a sealed ecosystem can support a human population for centuries. Living systems do not remain fixed. Plants adapt to their environment. Microorganisms mutate. Populations compete. A species that performs well during the first decade may behave differently after thousands of generations. Even a carefully selected crop can become a point of failure. Agricultural systems often prefer genetically similar plants because they grow at comparable rates and produce uniform harvests. That predictability simplifies lighting schedules, nutrient delivery, and processing. It also creates monoculture susceptibility. If the plants share similar genetic defenses, a pathogen capable of infecting, one may infect nearly all of them on Earth. Genetic diversity across farms, regions, and seed banks limits some of that risk. A Starship carries only the diversity that fits inside its biological archive. The rhizosphere presents another danger. This is the zone around plant roots where water, minerals, root secretions, and microorganisms interact. Some microbes support nutrient availability or protect roots. Others compete with the plant or cause disease. If disinfectants remove too many organisms, beneficial functions may disappear. If control becomes too weak, opportunistic species may dominate. A rhizosphere collapse can occur without a dramatic invasion. The microbial balance can shift until roots no longer absorb nutrients effectively, even while those nutrients remain present in the solution. This resembles nutrient lockout. Nitrogen, phosphorus, or micronutrients may exist in the farm, but in a chemical form, concentration or acidity range that roots cannot use efficiently. Adding more fertilizer does not necessarily solve the problem. It may increase salt stress or worsen the imbalance. Plants also release chemicals of their own. Through allelopathy, compounds produced by one plant can influence the germination or growth of another on Earth. Rain, soil volume, and microbial degradation may dilute those compounds. In a closed hydroponic loop, they can recirculate. Pollination is another narrow bridge. Some crops self-pollinate. Others require vibration, airflow, insects, or manual assistance. A failure in timing can eliminate fruit and seed production for an entire cycle. Even when every plant appears healthy, then there is the seed archive. Seed viability declines according to species, moisture content, temperature, oxygen exposure, and storage duration. Cryogenic storage may extend useful life for some material, but the refrigeration system requires continuous power and maintenance. Seeds also carry microorganisms on their surfaces and within their tissues. The biological backup can bring the next disease into the farm. The ship therefore faces a paradox. A simplified ecosystem is easier to model. Fewer species create fewer interactions. Control systems can maintain narrow ranges of temperature, humidity, carbon dioxide, acidity, and nutrient concentration. But a simple ecosystem has little ecological redundancy. If one species performs a critical function and disappears, nothing replaces it. A diverse ecosystem may contain organisms capable of compensating for disturbance. It may resist some pathogens and recover from stress, yet every additional species introduces new interactions, competition, and behavior that may be difficult to predict. Too much control can create fragility. Too much freedom can create instability. The Starship must do more than grow food. It must manage biological change across decades without allowing adaptation, mutation, or ecological competition to push the farm beyond its safe operating range. The white growth around the roots is finally contained. Contaminated trays are isolated. Nutrient lines are sterilized. New seedlings begin to rise beneath the lamps. The harvest may recover, But another threat is already passing through the leaves. The water tanks, the crew's bodies, and the computers controlling the farm. It arrives as atomic nuclei, moving with enough energy to damage matter from within. There is no sound when an iron nucleus enters the ship. It passes through the outer shield, through wiring and processor boards, through layers of water and polymer, then through living tissue. Along its path, it leaves a dense trail of ionization at the scale of molecules and cells. Chemical bonds break. Electrons are stripped from atoms. Secondary particles scatter away from the collision. Then the nucleus is gone. No flash crosses the cabin. No crew member feels the impact. The ship continues operating as if nothing happened. But something has changed. Space radiation is not one uniform threat. Solar particle events erupt from the sun. They can produce intense streams of energetic protons over hours or days. Their arrival is episodic, near the sun. Monitoring may provide enough warning for a crew to move into a heavily shielded storm shelter. Galactic cosmic rays are different. They arrive from beyond the solar system. Most are protons. A smaller fraction consists of helium nuclei. An even smaller population contains the bare nuclei of heavier elements, including carbon, oxygen, silicon, and iron. These heavy particles are uncommon compared with protons. But rarity does not make them harmless. Many belong to a category known as high charge and high energy particles. They carry substantial electrical charge and move at enormous velocities. As they pass through matter, they can produce concentrated ionization along a narrow track. This is where linear energy transfer becomes important. Linear energy transfer describes how much energy a particle deposits into material over the distance it travels. A low LET particle may spread its energy across a longer path. A high LET heavy ion can deposit a dense concentration of energy through a small volume of tissue. The biological result is not determined only by total dose. It also depends on how that dose is distributed. During the Curiosity rover's journey to Mars, its radiation assessment detector measured an average galactic cosmic ray dose equivalent of approximately 1.8 millisieverts per day inside the spacecraft. That was during a voyage lasting months. NASA's current radiation protection requirements state that habitable space systems designed to support a crew for more than 60 days should protect crew members from galactic cosmic radiation to an effective dose rate below approximately 1.3 millisieverts per day. The requirement is paired with the principle known as a LARA exposure, must be kept as low as reasonably achievable. But that figure is not a declaration that 1.3 millisieverts per day is safe for 40 years. It is a design threshold created for present human spaceflight programs. A voyage lasting decades would extend exposure far beyond the duration of existing crewed missions and far beyond the direct human data available from deep space. The numbers cannot simply be multiplied and treated as a precise medical prediction. Radiation risk depends on particle type, energy, organ sensitivity, age, biological sex, shielding geometry, and uncertainty in long-term effects. Still, the direction of the problem is unmistakable. Exposure accumulates. At the molecular level, radiation can ionize water inside cells and create reactive chemical species. These molecules can damage proteins, membranes, and DNA. Some DNA damage involves a single altered base or a break in one strand. Cells possess repair mechanisms capable of correcting many of these injuries. High LET particles can create clustered DNA damage. Several lesions may occur close together, multiple strand breaks, damaged bases, and altered sugar phosphate structures within a compact region. This is harder for cellular repair machinery to reconstruct correctly. A cell may die, it may stop dividing, or it may survive with a mutation. Across years, those outcomes can contribute to cancer risk, tissue degeneration, and changes in organ function. Researchers also study possible effects on the cardiovascular system, the lens of the eye, and the central nervous system. The uncertainty does not remove the hazard. It makes planning harder. A shield can reduce exposure, but radiation shielding is not as simple as placing more metal between the crew and space. When a high-energy cosmic ray nucleus strikes an atomic nucleus in the hull, the collision can break both into smaller fragments. This process is called nuclear spallation. The original particle may disappear, but the impact produces secondary radiation. Neutrons, protons, and lighter nuclear fragments continue through the spacecraft. Some secondary particles may penetrate deeper than expected, or deliver biologically significant doses in locations the original particle would not have reached. This is one reason shielding material matters. Aluminum is widely used in spacecraft because it is strong, relatively light, and well understood. But its atomic nuclei can produce complex secondary particle fields when struck by energetic cosmic rays. Hydrogen-rich materials often perform better against important parts of the radiation spectrum. Hydrogen nuclei are simple protons, so interactions tend to generate fewer heavy nuclear fragments than collisions with higher mass elements. Polyethylene contains large amounts of hydrogen. Water does too. A starship could position water tanks, food, waste, awaiting processing, and other hydrogen-rich supplies around sleeping quarters or a central shelter. The same mass required for life support would then serve a second purpose. But every arrangement creates trade-offs. A storm shelter concentrated around water may protect against a solar particle event. Galactic cosmic rays arrive continuously and from many directions. They do not wait for the crew to enter a shelter. The crew cannot spend 40 years inside a cramped central vault. Radiation also changes as shielding thickness changes. A configuration optimized for lower energy solar protons may not provide the same benefit against the broad, high-energy GCR spectrum. Additional mass can reduce some components while producing different secondary particles. There is no single magical thickness that solves every case. Active magnetic shielding has been proposed as another approach because many cosmic ray particles carry electrical charge. A sufficiently strong magnetic field could bend their trajectories before they reach the habitat. Concepts using superconducting magnets continue to be studied. Yet a practical system would require large field volumes, substantial structural support, electrical power, and long-term cryogenic operation. Superconducting coils would have to remain reliable for decades. A magnet quench could release stored energy as heat and mechanical stress. Neutral particles, including neutrons, would not be deflected by a magnetic field. Active shielding remains research, not a proven protective system for a crewed interstellar ship. The radiation threat does not stop at the human body. It enters the farm. Seeds exposed over long periods may accumulate molecular damage. Some damage prevents germination. Some affects growth. Some mutations remain hidden until later generations. Microorganisms are exposed as well. Bacteria and fungi can adapt quickly because their generations are short. Radiation may kill many cells while selecting for survivors with different traits. Those survivors may interact differently with roots, filters, disinfectants, or human immune systems. Then radiation reaches the electronics. A single energetic particle can deposit enough charge in a memory cell to change its stored state. A 0 becomes a 1. This is a single event upset. Error-correcting memory can detect and repair some of these changes. But another event may produce a single event latch-up, creating an abnormal current path through a semiconductor. If protective circuitry does not interrupt the current quickly, the component can overheat and suffer permanent damage. Beyond individual events lies total ionizing dose. Radiation gradually traps charge inside insulating layers and alters semiconductor behavior. Leakage current rises, switching thresholds shift, noise increases. A processor that once operated reliably at full speed may require lower voltage margins, reduced clock rates, or eventual replacement. The same radiation field is therefore attacking 4 foundations of the mission at once: the crew, the seeds, the microorganisms, the computers. The Starship is not merely growing older, Every living and mechanical system responsible for keeping it alive is being forced to age together. Water and polyethylene may reduce part of the exposure. Redundant processors may correct part of the damage. Medicine may treat some of the consequences. But no shield can stop time. After several years, the most dangerous enemy no longer needs to arrive from another star. It begins to appear inside bearings, welds, electrical contacts, and every temporary repair holding the ship together. One failed component can be replaced. 100 failures can be managed. But when a pump fails, because electrical power has weakened because the cooling system is degrading, and the cooling system cannot be repaired because the crew is sick. The ship has entered a form of decline with no single cause. In year 18, a circulation pump begins to fail. Its bearings produce a low vibration. Flow through the thermal control loop becomes unstable. Temperatures rise inside a bank of power electronics. The crew replaces the pump. Flow returns to normal. Temperatures fall. The repair is recorded as one of the year's major successes. 2 years later, a coolant line cracks in the neighboring compartment. The investigation eventually finds the cause. The replacement pump was almost correct, but not perfectly balanced. Its vibration remained within the allowable limit for the pump itself. Yet that vibration traveled through the mounting structure and entered a pipe support that had already endured 2 decades of thermal cycling. The repair that saved the ship in year 18 helped create the crisis of year 20. This is how an interstellar vessel grows old. A new spacecraft begins with design margins. Pipes tolerate more pressure than normal operation requires. Electrical cables carry less than their maximum current. Pumps have reserve capacity. Structures are built to survive loads greater than those expected during the mission. Those margins are not permanent. Every operating cycle consumes a small part of them. Fatigue crack propagation begins with a microscopic defect. It may form at a machining mark, a weld, a sharp corner, or an inclusion inside the material. Repeated loading opens and closes the defect. Each cycle extends the crack by an almost invisible amount. For years, nothing appears wrong. Then the remaining intact material becomes too small to carry the load. Growth accelerates. A component that survived millions of cycles can fail after only a few more. Thermal cycling creates another clock. When machinery warms, its materials expand. When it cools, they contract. Different materials expand by different amounts at a joint between metal, ceramic, and polymer. That mismatch creates stress. Solder joints develop cracks. Seals change shape. Bolted interfaces loosen. Electrical connections become intermittent. A component does not need to move mechanically to experience fatigue. Temperature can provide the repeated load. Creep operates more slowly. Under constant stress, some materials gradually deform, especially at elevated temperatures. A pipe wall can stretch. A turbine blade can change shape. A seal compressed for decades may no longer recover when pressure is removed. Radiation adds another form of aging. Energetic particles displace atoms and alter molecular bonds. Polymers may become brittle. Insulation may lose flexibility. Some metals experience changes in strength, ductility, or dimensional stability depending on material, dose, and temperature. In vacuum, polymers and lubricants face outgassing. Volatile molecules escape from adhesives, cable insulation, coatings, and seals. The material left behind may shrink or harden. Escaped compounds can later condense on cooler surfaces, including optical instruments and thermal radiators. Lubricants also migrate. A thin oil film can slowly move away from a bearing surface through capillary effects, evaporation, or temperature gradients. Grease can separate into components. Solid lubricants can wear through. Even equipment that remains motionless is not necessarily protected. A bearing supporting a static load can develop small permanent depressions where its rolling elements press against the race. This is Brinelling. When the bearing finally rotates, those depressions produce vibration, noise, and accelerated wear. Corrosion remains possible as well. Two dissimilar metals connected in the presence of a conductive liquid can form a galvanic couple. One becomes more vulnerable to corrosion. In a water loop, a tiny leak or contaminated condensate can provide the electrolyte. The damage may begin beneath insulation or inside a joint where inspection is difficult. Engineers attempt to predict these failures before launch. Failure mode and effects analysis lists the ways each component might fail and traces the consequences. Fault tree analysis begins with a dangerous outcome and works backward through combinations of events capable of producing it. Meantime between failures provides a statistical description of reliability for repairable equipment. But MTBF is not a warranty date. A pump with a long MTBF can still fail during its first year. The value describes a population or an operating history, not the guaranteed lifetime of one specific unit. A Starship contains thousands of components. Even if each is individually reliable, the probability that something is approaching failure remains high because so many devices are operating at once. Reliability therefore depends on architecture. Graceful degradation allows a system to lose part of its capacity without losing its entire function. A farm might dim one lighting bank while keeping critical crops alive. A computer cluster might shut down damaged processors and continue at reduced performance. Fault containment regions are designed to stop one failure from spreading. A leaking coolant loop is isolated. A damaged power bus is disconnected. A software fault is confined to one partition. But containment is never perfect. A cooling loop may be isolated mechanically, while its loss forces the electrical system to reduce output. Lower power then affects water treatment, lighting, and medical equipment. This is a cascading failure. A common mode failure is more dangerous. Several supposedly independent systems fail for the same reason: the identical software, shared cooling, the same contaminated material, or a design assumption that was wrong from the beginning. As the voyage continues, repairs create a new problem. Physical technical debt accumulates. The replacement pipe follows a different route because the original access path is blocked. A substitute alloy has slightly different thermal expansion. A sensor is disabled because no compatible unit remains. Software receives another exception to accommodate modified hardware. A temporary manual valve becomes permanent. Operating procedures gain handwritten steps. Diagrams no longer match the ship. Maintenance records describe what changed, but not always why. After enough repairs, the crew is no longer operating the vessel that left Earth. It is operating a machine rebuilt by thousands of emergency decisions. Each decision may have been reasonable alone. Together, they create interactions no original model predicted. This leads to the point of no return in maintainability. It is not the moment when the ship loses power or the atmosphere becomes toxic. It is the moment when faults begin appearing faster than the crew can identify, prioritize, and repair them. The maintenance backlog grows. Preventive inspection is postponed to handle emergencies. Postponed inspection allows hidden damage to develop. Emergency repairs consume more spares and create more technical debt. The crew works harder but falls further behind. The ship may continue for years after crossing this boundary. Lights still turn on. Crops still grow. Displays still report acceptable numbers. Yet the outcome has begun to lock into place. Every day removes another option. Every unresolved fault reduces the margin available for the next one. Recovery remains theoretically possible, but the resources needed to achieve it are disappearing faster than they can be restored. To push that boundary farther away, the Starship must do something no factory has ever sustained in complete isolation. It must manufacture replacement parts for itself, using material recovered from the components that have already died. The pressure valve is no longer in storage. The last certified spare was installed 11 years earlier. A second unit was disassembled to repair another system. No compatible valve remains anywhere on the ship, so the factory begins to feed on the vessel around it. A low-priority assembly is removed from an inactive compartment. Its metal is identified, cleaned, and broken down. The alloy is remelted. Its composition is adjusted. New feedstock is prepared. A replacement valve is manufactured. Its dimensions are correct. Its surface is smooth. It passes the first pressure test inside the metal. However, a pore smaller than a human hair remains hidden near a region of maximum stress. The valve looks perfect. It is not. Additive manufacturing is often described as the solution to spare parts in deep space. A digital file exists. A machine deposits material. A new component appears. But printing a shape is only one stage of manufacturing. A self-sufficient Starship needs an industrial chain. First, recovered material must be sorted. Aluminum cannot be casually mixed with titanium. Stainless steels contain controlled amounts of chromium, nickel, carbon, and other elements. High-performance alloys may depend on trace additions measured in fractions of a percent. The material must be cleaned. Oil, paint, oxide, biological residue, and fragments of other alloys can contaminate the melt. Some impurities create brittle phases. Others change corrosion resistance or interfere with welding. The metal is then refined and remelted. Its chemical composition must be measured and corrected. Elements lost through oxidation or evaporation may have to be replaced. Only then can the material become powder, wire, sheet, or stock suitable for manufacturing. Powder-based additive systems require particles with controlled size and shape. Poorly flowing powder creates uneven layers. Moisture and oxygen can alter reactive metals. Reused powder changes after repeated exposure to heat. Once the component is printed, it is still unfinished. Machining may be required to create precise sealing surfaces and bearing fits. Heat treatment changes the microstructure and relieves part of the internal stress. Hot isostatic pressing can expose a metal part to high temperature and pressure from all directions, helping close internal pores. Surface finishing removes roughness that could initiate fatigue cracks. Then comes metrology. The component's dimensions, geometry, and surface quality must be measured against requirements. A valve seat that is wrong by a small amount may leak. A bearing bore that is slightly misaligned may create vibration. Dimensional accuracy is not enough. Non-destructive evaluation must search for hidden defects without destroying the part. Depending on the material and geometry, the factory may need ultrasonic inspection, radiography, eddy current testing, dye penetrant inspection, or computed tomography. Only after inspection can the component be certified for use. Each step requires its own equipment, calibration standards, energy, software, and expertise. The reason is porosity. During additive manufacturing, incomplete melting, trapped gas, or unstable process conditions can leave voids inside the material. A pore concentrates stress around its edge. Under repeated loading, it can become the starting point for a crack. Residual stress creates another danger. Additive processes heat and cool small regions rapidly. One layer solidifies while the next is melted above it. Different regions attempt to expand and contract at different times. The finished component can contain locked-in stress even when no external load is present. It may distort during machining or crack during service. Anisotropy means that material properties differ according to direction. A printed component is built layer by layer. Its strength and fatigue resistance may not be identical along the build direction and across the layers. Orientation therefore becomes part of the engineering design. The grain structure also matters. Metals are made of crystalline regions separated by grain boundaries. Grain size, orientation, and boundary chemistry influence strength, corrosion, and resistance to crack propagation. A part can have the correct external dimensions while possessing the wrong internal metallurgy. Fatigue life describes how long it can survive repeated loading. Fracture toughness describes its resistance to the growth of an existing crack. Both can be damaged by poor processing, contamination, or the wrong heat treatment. Recycling introduces a slow contamination problem. Trace elements accumulate. A small amount of copper enters an aluminum stream. Carbon changes in a steel melt. Oxygen rises in a titanium alloy. One recycling cycle may produce acceptable material. Repeated cycles can move the composition outside its safe range. The factory may respond through downcycling. High-quality aerospace alloy becomes material for lower stress brackets. Later, those brackets become shielding blocks or counterweights. The metal remains useful, but it cannot return forever to the most demanding applications. This means recycling is not perfectly circular. Quality tends to flow downward unless the ship can separate impurities and restore precise composition. Some materials are far harder to reproduce than structural metal. Catalysts depend on controlled surface area, pore structure, and chemical composition. Semiconductor manufacturing requires extraordinary purity, nanoscale patterning, and tightly controlled environments. Biomedical sensors combine specialized polymers, enzymes, membranes, and electronics. Pharmaceutical production requires chemical synthesis or biological processing, purification, sterility, and analytical testing. Medical-grade polymers must remain biocompatible. High-performance lubricants may require molecules and additives the ship cannot synthesize. Superconducting materials, permanent magnets, and advanced optical coatings demand processes far beyond a simple machine shop. Trace elements create another bottleneck. A material may need only a tiny amount of a rare element. But if that element is lost into mixed waste or slag, the ship may have no economical way to recover it. Mass still exists. Useful composition does not. Then the factory faces its own mortality. Its laser optics degrade. Bearings wear. Vacuum pumps lose performance. Position sensors drift. Furnaces develop temperature gradients. Inspection equipment falls out of calibration. The factory can produce parts for the ship. But what produces parts for the factory? This question becomes terrifying when measurement begins to drift. Suppose the coordinate system of a machining center shifts by a fraction of a millimeter. Every component it produces may carry the same error. If the inspection machine was calibrated against the same damaged reference, the defect may pass unnoticed. The factory can manufacture hundreds of identical failures. One inaccurate standard becomes a fleet-wide, common-mode fault. The solution is not merely more manufacturing. The vessel needs a technical immune system. Sensors detect abnormal vibration, heat, pressure, or chemistry. Diagnostic systems distinguish the failed component from the symptom it created. The factory produces a replacement. Independent inspection rejects hidden defects. Finally, the ship records what happened. The cause, the repair, the altered design, and the evidence must enter a living technical memory. That knowledge becomes the equivalent of an antibody, allowing the vessel to respond faster if the same pattern returns. But an immune system works only if it can identify the threat correctly. After decades of radiation exposure, sensor drift, and software modification, the ship's electronic brain may no longer be able to distinguish a real failure from corrupted data. 3 computers receive the same signal. 2 conclude that the ship has drifted off course. The third reports that the navigation sensor is malfunctioning. The control system uses majority voting. 2 against 1. Thrusters are ordered to fire. What the voting logic does not know is that the first 2 computers use the same corrupted software library. They agree because they share the same mistake. The third computer is correct. Redundancy is one of the foundations of spacecraft engineering. A critical decision should never depend on a single processor, a single wire, or one memory device. But redundancy is not the same as truth. Digital information is stored as physical states inside electronic components. Those states can be changed by radiation, electrical noise, aging hardware, or software faults. A high-energy particle does not need to destroy a processor to alter its behavior. It may deposit enough charge inside a memory cell to change one stored bit. A 0 becomes a 1. If that bit belongs to an image, the result may be a discolored pixel. If it belongs to a navigation coordinate, valve command, or memory address, the consequences can be much larger. Error-correcting code memory helps protect against this. Additional information is stored alongside the original data. The system uses that information to detect and correct certain patterns of bit errors. A common design can correct a single bit error in a protected word and detect some multi-bit errors. But correction has limits. If several nearby bits change before the memory is checked, the system may detect damage without being able to reconstruct the original value. In some cases, a sufficiently complex corruption can appear valid. That is why memory scrubbing is used. The computer periodically reads stored data, checks it for errors, repairs what it can, and writes the corrected information back. Scrubbing prevents isolated radiation-induced faults from accumulating quietly until they become uncorrectable. Processors can also be arranged in triple modular redundancy. 3 units perform the same calculation. A voter compares their outputs. If one disagrees with the other 2, the majority result is accepted. This works well when failures are independent. It becomes dangerous when 2 processors contain the same software defect, receive the same corrupted input, or were manufactured with the same hidden weakness. The vote then measures agreement, not accuracy. Diverse redundancy attempts to reduce that risk. One computer may use a different processor architecture. Another may run independently developed software. A third may calculate the same answer through a different method. Diversity makes common failure less likely. It also makes the system more difficult to maintain. Different architectures require different tools, spare components, and expertise. Software written by separate teams can interpret the same sensor data in subtly different ways. The ship must manage both uniformity and diversity. Checkpointing provides another defense. The computer periodically saves a verified state. If later behavior becomes unstable, the system can perform a rollback, returning to an earlier configuration known to have worked. A watchdog timer monitors whether software continues responding. If a program becomes trapped in an endless loop or a processor stops producing expected signals, the watchdog can force a reset, but restarting is not always recovery. If the saved checkpoint already contains corrupted assumptions, rollback restores the error. If a faulty sensor keeps sending the same misleading data, the restarted computer reaches the same wrong conclusion. Radiation-hardened electronics reduce vulnerability by using specialized materials, larger transistor geometries, protective circuit designs, and manufacturing processes. Selected for tolerance rather than maximum speed, they are often slower and less energy efficient than the most advanced commercial processors on Earth. That trade is deliberate. A Starship does not need a processor that wins a benchmark for 6 months. It needs one that remains predictable after years of accumulated radiation. Even hardened electronics eventually age. Total ionizing dose changes transistor thresholds. Insulating layers trap charge. Leakage current rises. Timing margins shrink. A circuit that once completed an operation safely within 1 clock cycle may begin returning unstable results. Then comes the Byzantine problem. A failed component that stops responding is relatively easy to identify. Silence is clear. A Byzantine fault is different. The damaged component continues to communicate. It may send different answers to different systems. It may produce values that are wrong but plausible. It may behave correctly for weeks, then fail only under a rare combination of inputs. A temperature sensor stuck at an impossible value can be rejected. A sensor that reports 21.4 degrees when the true value is 24.8 may remain trusted. That difference can matter if the sensor controls a biological reactor, battery pack, or medication refrigerator. Navigation brings all of these uncertainties together. A star tracker captures images of the sky and compares the observed pattern with a stored catalog. From the positions of known stars, it determines the ship's orientation. But the sky is not fixed. Stellar aberration changes apparent positions because the ship is moving while light reaches its instruments. Parallax changes the geometry as the ship travels away from the solar system. A nearby star viewed from several light-years away no longer appears against exactly the same background. The reference stars themselves have proper motion. They move through the galaxy at different velocities. Over decades, a catalog created at launch must be propagated forward using measured stellar motion. Small uncertainties in those values can become significant when the ship has traveled trillions of kilometers. The inertial navigation system provides another estimate. Gyroscopes and accelerometers track rotation and acceleration without depending on an external signal. But every inertial sensor contains bias and noise. A tiny persistent error produces inertial drift. Over minutes, the difference may be negligible. Over years, it can become enormous unless corrected by external observations. External observations also degrade. Dust pits, optical surfaces, outgassed compounds form films on mirrors and lenses. Radiation creates defects in detector pixels. Thermal distortion changes alignment between the telescope and the body of the ship. The stars may be measured accurately by an instrument that is no longer pointing exactly where the computer believes it is pointing. Pulsar navigation has been studied as another possibility. Pulsars emit highly regular signals that could act as natural timing beacons. By comparing pulse arrival times from several sources, a spacecraft may estimate its position. The principle has been demonstrated experimentally in limited contexts. It is not a proven, complete navigation system for a crewed interstellar starship. The ship therefore combines star tracking, inertial measurements, astronomical models, and internal diagnostics. It may also maintain a digital twin. The digital twin is a computational representation of the physical vessel. It predicts temperatures, pressures, vibration, flow rates, power consumption, and component aging. If a pump's measured vibration rises faster than predicted, the model flags a possible bearing fault. If electrical demand increases without a matching operational change, the system searches for leakage or declining efficiency. The digital twin gives the ship a way to compare reality with expectation, but it can suffer model drift. After decades of repairs, the physical ship contains replacement alloys, rerouted pipes, modified software, and components operating outside their original specifications. If the model is not updated correctly, it continues predicting the behavior of a vessel that no longer exists. The discrepancy may be interpreted as a bad sensor. In reality, the sensor may be accurately describing a ship whose structure has changed. The greatest navigation threat is not that the starship becomes lost. It is that the ship calculates the wrong position, confirms that answer through several systems, and becomes certain. A computer can be restarted. A human body cannot, and when the only physician becomes seriously ill, the ship loses both a patient and the person expected to save that patient. The reactor engineer needs surgery. The diagnosis cannot be delayed. Without treatment, the condition may become fatal. The only crew member qualified to perform the operation is also the ship's senior water recovery specialist. If the surgery fails, the vessel may lose more than one life. It may lose two critical fields of knowledge at the same time. On Earth, modern medicine is a network. A patient moves between primary care, imaging, pathology, surgery, intensive care, rehabilitation, and specialist consultation. Blood products arrive from donors. Sterile supplies come from manufacturers. Laboratories perform tests using equipment maintained by dedicated technicians. A starship has no network behind it. There is no medical evacuation. No sample can be sent to an outside laboratory. A specialist on Earth may answer, but years of communication delay make real-time consultation impossible. The ship cannot wait for instructions while a patient is bleeding. There is no pharmaceutical supply chain. No replacement scanner can arrive if an imaging system fails. No hospital can provide extra blood. No additional surgeon can be called into the operating room. The vessel must carry the equipment. knowledge and biological resources needed to manage every treatable condition for the entire voyage. That requirement is far larger than a room filled with medicine. Pharmaceutical stability depends on chemistry and environment. Temperature changes the rate at which molecules degrade. Humidity can alter tablets, powders, and packaging. Oxygen promotes oxidation. Radiation can break chemical bonds or damage biological products. Light affects photosensitive compounds. The container matters as well. A drug sealed in a high-barrier blister package may behave differently from the same compound stored in a multi-dose bottle that is repeatedly opened. Liquid formulations can degrade differently from dry powders. Reconstituted medication may remain usable for a much shorter period than its unopened form. Small molecule drugs are not automatically stable, but many are easier to store than complex biological products. Insulin, vaccines, antibodies, and other biologics depend on carefully folded proteins or sensitive biological structures. Heat can alter their shape. Freezing can damage some formulations. Repeated temperature excursions may reduce potency, even when the medicine looks unchanged. This creates a cold chain problem. Refrigeration requires continuous power. Compressors, pumps, seals, sensors, and control electronics must remain operational. A refrigerator failure can destroy years of medical reserves without damaging the packaging enough to make the loss visually obvious. Food adds another pharmaceutical burden. Vitamin C, vitamin K, folate, and thiamine can decline during processing and long-term storage. Nutritional deficiency may therefore emerge even when the crew receives sufficient calories. The medical system must distinguish disease from a failing food supply. A patient with fatigue, neurological changes, or poor wound healing may not need only medicine. The patient may be evidence that the ship's entire nutritional system is drifting outside its safe range. Producing pharmaceuticals on demand appears attractive, but it requires an industrial chain as demanding as metal manufacturing. A microbial strain or a mammalian cell line must remain genetically stable. A bioreactor must control temperature, acidity, oxygen transfer, and contamination. The desired compound must be separated from cells, proteins, toxins, and processing chemicals. Purification may require filtration, chromatography, and sterile transfer. The final product must be tested. Its identity must be confirmed. Its concentration must be measured. Impurities must remain below safe limits. Sterility assurance must show that bacteria, fungi, and harmful biological material have not entered the dose. A substance is not medicine merely because a bioreactor produced it. Bioprinting. Engineered microbes and compact pharmaceutical manufacturing remain important research areas. They cannot be treated as completed solutions for centuries of autonomous medical care. The crew's illnesses will also differ from those of a normal population on Earth. In reduced gravity or microgravity, bones lose mineral because mechanical loading changes. Osteoclast activity can exceed bone formation, releasing calcium and weakening skeletal structure. Muscles atrophy when they no longer work against body weight. The cardiovascular system adapts to altered fluid distribution. Balance and spatial orientation change as the vestibular system receives signals unlike those experienced on Earth. Exercise can reduce some effects, but exercise machines require maintenance, time, and electrical power. The immune system may also change during spaceflight. Stress, radiation, disrupted sleep, and altered microbial exposure can influence immune regulation. The ship is a closed microbial ecosystem. Human beings continuously shed bacteria and fungi into air, water, and surfaces. Some organisms remain harmless under normal conditions. Others become opportunistic when immunity weakens or when a wound, catheter, or surgical procedure creates a path into the body. Radiation introduces a long-term cancer risk, yet diagnosis and treatment require imaging, pathology, surgery, pharmaceuticals, and follow-up. Chemotherapy can suppress immunity in an environment where microbial control is already difficult. Radiotherapy equipment would be massive and technically demanding. Surgery may remove a localized tumor, but only if someone can identify it early and operate safely. Then there are ordinary emergencies. A complicated birth can threaten both parent and child. A dental abscess can spread infection. A fracture can remove a critical technician from duty for months. Appendicitis, kidney stones, and internal bleeding do not become simpler because the patient is traveling between stars. Mental illness may be even harder to manage. A patient experiencing severe depression, psychosis, aggression, or suicidal thinking cannot be transferred to a secure hospital. The patient remains inside the same confined community. Isolation protects the crew, but may worsen the illness. Sedating the patient may reduce immediate danger while removing a needed specialist from duty. Every clinical decision has consequences beyond medicine. This is why medical redundancy must be built into the population. The physician needs a successor. Every critical specialist needs at least one apprentice. Several crew members require cross-training in emergency procedures, anesthesia, imaging, infection control, and basic surgery. Robotic systems may stabilize instruments, filter tremor, or guide a procedure using stored plans. They can extend human capability. They do not eliminate the need for judgment. Real anatomy varies. Bleeding obscures the field. Scar tissue changes tissue planes. Unexpected complications force decisions no pre-written sequence can guarantee. A surgical manual does not make its reader a surgeon. Expertise is built through supervised practice, pattern recognition, and experience with uncertainty. A crew that stores medical information without preserving a living training tradition possesses books, not medicine. The reactor engineer survives the operation, but the event reveals the deeper danger. The ship does not merely have to preserve a population. It must protect the specific people who carry irreplaceable knowledge about the reactor, water loop, farm, factory, and navigation system. One death can begin a competency cascade. A specialist is lost. Maintenance quality falls. A neglected system fails. The failure causes injuries or disease. More experts are removed from duty. The remaining crew inherits a larger workload with less support. The ship begins losing knowledge faster than it loses hardware. By year 40, the most fragile system may no longer be the pump, reactor, or hospital. It may be the chain of knowledge connecting the people who once saw Earth with the children who know it only through images. The first generation calls the Starship a vehicle. The second calls it home. By the 10th generation, the destination may have become an ancient story. Earth may have become a religion. The control room may contain switches no one remembers why they must never touch. But for the first crew, the journey has lasted only one lifetime. After more than 4 decades, the star ahead finally begins to look different from the others. It grows brighter. Its motion against the background becomes visible. The crew has reached the end of 4.24 light-years of darkness. Then new data arrives. The planet that pulled the ship across interstellar space may have no substantial atmosphere. Proxima Centauri is the closest known star to the Sun. It is part of the wider Alpha Centauri system and lies approximately 4.24 light-years away. That sounds close only because every other star is farther. Light, moving at nearly 300,000 kilometers per second, needs more than 4 years to cross the distance. A spacecraft traveling at an ideal cruise velocity of 10% of light speed would require roughly 42 years. That is only the simplest transit estimate. The ship cannot instantly jump to its cruise velocity. It must accelerate. It must later turn or redirect its thrust and decelerate. Finally, it must approach the target with enough precision to enter a useful trajectory. Every acceleration profile adds time, energy demand, and structural load. No propulsion system has demonstrated the ability to carry a crewed spacecraft to 10% of light speed. NASA-supported studies of beamed propulsion have explored the possibility of pushing extremely light probes with powerful external beams. Some concepts use lasers to accelerate thin sails attached to gram-scale spacecraft. The mass difference is decisive. A probe weighing a few grams does not need an atmosphere, radiation shelter, hospital, farm, or braking system for a human settlement. A Starship might weigh thousands or millions of tons once shielding, machinery, propellant, and living space are included. A propulsion concept that accelerates a wafer-sized probe does not prove it can move a civilization. Still, Proxima Centauri remains the most tempting destination because it has at least one confirmed planet in the star's habitable zone. Proxima b was detected through the radial velocity method. Astronomers observed small changes in the star's motion caused by the planet's gravitational pull. That method establishes a minimum mass rather than a direct physical size. The available measurements place Proxima b in a mass range consistent with a terrestrial planet, but many of its properties remain unknown. The phrase habitable zone is often misunderstood. It describes the range of orbital distances where a planet could maintain liquid water at its surface if it possesses suitable atmospheric conditions. It does not confirm that water is present. It does not confirm oxygen, oceans, soil, life, or even an atmosphere. Proxima b orbits a red dwarf. The planet is much closer to its star than Earth is to the Sun. That close orbit exposes it to a very different stellar environment. Proxima Centauri is magnetically active and produces powerful flares. A flare can release intense ultraviolet and X-ray radiation. Energetic particles may follow over long periods. This activity can influence atmospheric chemistry and escape. At the top of an atmosphere, energetic radiation can ionize atoms and molecules. Electrons are removed. Charged particles become vulnerable to interactions with the star's magnetic field and stellar wind. Light elements escape most easily. Hydrogen can be lost directly from the upper atmosphere. Water vapor broken apart by ultraviolet radiation can therefore lead to hydrogen escaping, while oxygen remains, reacts with surface minerals, or is removed through other processes. Atmospheric loss is not one simple event. Thermal escape, ion pickup, sputtering, and photochemical processes can act together. The outcome depends on the planet's gravity, magnetic environment, atmospheric composition, and the history of the star's activity. Proxima b may retain an atmosphere. It may possess only a thin one, or it may be an exposed world that lost much of its volatile inventory long before the ship left Earth. No telescope has yet directly confirmed which description is correct. The journey itself presents another hazard. Interstellar space is not empty. It contains gas, plasma, and dust. At ordinary spacecraft velocities, individual dust grains are small impact hazards. At a significant fraction of light speed, they become hypervelocity projectiles. NASA has tested spacecraft shielding by firing a 10-millimeter aluminum sphere into a representative ISS shield at approximately 5.67 kilometers per second. The impact helped engineers study penetration, fragmentation, and repair techniques. A Starship at 10% of light speed would move at roughly 30,000 kilometers per second. That is more than 5,000 times the laboratory impact velocity. The comparison does not mean damage simply becomes 5,000 times worse. It means the collision enters a profoundly different physical regime. At extreme speed, the dust grain and part of the shield may ionize. Solid material becomes expanding plasma. Shock waves propagate through the structure. Secondary fragments spread beyond the original impact point. A Whipple shield uses a thin outer bumper to break or vaporize a projectile before the debris reaches the pressure wall. It is effective against many orbital debris threats at much lower velocities. Its success in Earth orbit cannot automatically be extended to interstellar speed. A Starship may require multiple sacrificial layers, thick forward shielding, active detection, and a structure designed to replace eroded sections. Even then, the dust distribution along the route cannot be mapped perfectly before departure. Every impact consumes part of the shield. By arrival, the forward face may be one of the oldest and most damaged systems on the ship. Then the crew must confront the destination. If Proxima b has no useful atmosphere, the planet cannot receive them as settlers stepping into open air. They would need sealed habitats, radiation protection, power generation, and closed-loop agriculture. In other words, they would need to rebuild the ship on the surface. If the planet is tidally locked, one hemisphere may face the star continuously, while the other remains in darkness. An atmosphere or ocean could redistribute heat, but without them, the temperature contrast could be severe. The crew may find no biological refuge, only another enclosed world. Alpha Centauri is the easiest interstellar destination by distance. But proximity guarantees nothing about habitability. The Starship may complete the greatest engineering achievement in human history and deliver its crew to a second prison. And if 42 years can demand the sacrifice of an entire adult life, a journey lasting 400 years creates a different moral problem. It asks roughly 20 generations to live inside a decision that only the first generation was allowed to make. The child born in the 2nd century has never seen a sky. It has seen images of blue atmosphere, white clouds and sunlight reflected from an ocean. It has heard recordings of rain, but the only ceiling it knows is metal. The child was not born solely because two people wanted a family. A population model predicted that the ship would face a shortage of reactor engineers 25 years later. Its future is already being discussed before it can speak. Talent will matter. So will oxygen production, food capacity, water recovery, and the number of trained adults expected to remain alive when the child reaches working age. At a distance of roughly 40 light-years, the TRAPPIST-1 system turns this ethical problem into a mission requirement. TRAPPIST-1 is an ultra-cool red dwarf with 7 known rocky planets close to Earth in size. Several orbit in or near the star's traditional habitable zone. At 10% of light speed, the simplest cruise estimate approaches 400 years. Acceleration and deceleration would add further demands. 4 centuries is long enough for approximately 20 human generations if the average interval between generations is around 20 years. The exact number would depend on reproductive timing and longevity, but the central reality remains unchanged. Almost everyone who lives aboard the vessel will be born there and die there. The first crew may choose the mission. Their descendants cannot, nor can the ship guarantee that the destination will justify the sacrifice. By early 2026, the James Webb Space Telescope had collected data for all 7 TRAPPIST-1 planets, while reported analyses had focused on several of the inner worlds. Webb had found no evidence of a thick atmosphere on TRAPPIST-1, B, or C. The data suggested that B may be a bare rock and that any atmosphere around C would likely be thin. For TRAPPIST-1, D, and E analysis remained incomplete. Scientists had ruled out thick hydrogen-dominated atmospheres, but had not established that either planet possessed an atmosphere capable of supporting habitable surface conditions. No TRAPPIST-1 planet has been confirmed as habitable. The ship would therefore be committing centuries of human life to a target whose most important environmental properties might remain uncertain at departure. The population inside must survive long enough to learn the answer. That begins with genetics. A founding crew carries only part of humanity's total genetic diversity. This is the founder effect. Alleles that are common in the wider human population may be rare or absent aboard the ship from the beginning. In a small population, genetic drift becomes powerful. Allele frequencies can change through chance rather than biological advantage. If one person has no children, an entire set of genetic variants may disappear from the population over generations. Related individuals become more likely to reproduce. The inbreeding coefficient describes the increasing probability that 2 copies of a gene are inherited from a common ancestor. As that probability rises, recessive disorders can appear more often because harmful variants are more likely to be paired. The total number of people does not tell the whole story. Geneticists also consider effective population size, the number of individuals who actually contribute genes to future generations. A ship may contain 1,000 people, but if reproduction is highly uneven, its effective population size may be far smaller. Differences in sex ratio, family size, and survival can all reduce it. Immune diversity adds another concern. Human leukocyte antigen genes help the immune system present fragments of pathogens to immune cells. A population with broader HLA diversity can recognize a wider range of biological threats. If diversity contracts, the community may become more uniformly vulnerable to a pathogen or mutated microorganism already living within the ship. Cryopreserved sperm, eggs, or embryos could broaden the genetic reservoir beyond the active crew. But this is not a passive backup. Cryogenic storage requires reliable cooling, monitoring, and power. Containers must remain sealed. Samples must be protected from radiation and temperature excursions. Records linking genetic material to medical history must survive centuries. There are also questions of consent. Who is authorized to use the material after the donors are dead? Does a governing council choose which genomes enter the population? Can descendants reject reproductive policies created before their birth? No single minimum population can be presented as a universal solution. The required number depends on age structure, mortality, fertility, stored genetic material, reproductive strategy, voyage duration, and the medical ability to identify inherited disease. The demographic problem is just as unforgiving. Too few births create an aging population. The number of workers declines while maintenance demands remain constant. Skill gaps appear. Each surviving adult carries more operational responsibility. Too many births exceed the vessel's ecological capacity. Children need food, water, oxygen, space, medical care, and education. Agricultural output cannot expand without more lighting, nutrients, and electrical power. Carbon dioxide removal and waste processing have fixed limits. Timing matters as much as total population. If too few children are born during one decade, the ship may later lack apprentices for critical professions. If too many are born together, the education and food systems may be overloaded before those children become productive adults. Career assignment becomes a moral crisis. The vessel needs physicians, reactor specialists, biologists, machinists, teachers, and navigation experts in every generation. Personal aptitude can guide training, but the ship may not have the luxury of unlimited choice. A child who wants to become an artist may be told that the water system needs another chemist. A gifted physician may be required to train as a reactor operator because no one else can fill the future vacancy. Coercion may improve short-term survival while damaging the legitimacy of the society enforcing it. A population controlled entirely by algorithms could remain within resource limits. It could schedule births, assign occupations, and restrict relationships. It might also create resentment, resistance, and political violence. A starship that preserves human bodies by eliminating meaningful human freedom may arrive technically successful and morally destroyed. The mission is supposed to carry civilization to another star. Civilization means more than metabolism. It includes consent, dignity, curiosity, love, disagreement, and the right to build a life that is not merely a maintenance assignment. Population can be managed through birth schedules. Genes can be preserved in cryogenic storage. Expertise cannot be frozen in liquid nitrogen. It must pass through living minds, one generation at a time, without a single critical link being allowed to break. The reactor startup procedure is still read exactly as written. Every word is pronounced correctly. Every switch is touched in the prescribed order. Step 7 comes before Step 8. No one remembers why. For generations, the procedure has worked. Then a sensor produces a condition the manual never described. The automation stops and requests human judgment. The crew has the instructions. It no longer has the understanding needed to go beyond them. The ship still possesses data. Knowledge has died. These are not the same thing. Data is the raw record, a temperature, a pressure reading, a timestamp, the vibration spectrum of a pump recorded during year 12. Information appears when those records are organized. Temperatures are placed on a timeline. Pressure changes are connected to valve positions. The vibration spectrum is labeled and stored with the maintenance history. Knowledge explains relationships. It shows why the temperature rose, how the pressure change affected the coolant loop, and which bearing defect produced a particular vibration pattern. Expertise goes one step further. It allows a person to confront a situation that has never happened before. An expert recognizes incomplete patterns, questions bad assumptions, and adapts old knowledge to new conditions. A library can preserve data, information, and written explanations. It struggles to preserve expertise. Expertise is partly explicit. It can be described in equations, diagrams, and manuals, but much of it is tacit. It develops through practice, observation, correction, and failure. An experienced engineer hears a change in a pump before the diagnostic system flags it. A surgeon feels that tissue resistance is wrong. A farmer recognizes stress in a plant before its leaves show obvious damage. Those judgments are difficult to encode completely. They must be transferred between living people. That transfer can fail through skill decay. A procedure practiced every week remains familiar. A procedure used once in 30 years becomes theoretical. The crew may pass written examinations, yet freeze when the real system behaves differently from the simulator. Automation can make the problem worse. For decades, software keeps the reactor stable. Human operators monitor it, but rarely intervene. Each generation becomes more confident in the automation and less capable of replacing it. This is automation complacency. The system appears so reliable that manual skill no longer feels urgent. Training hours are reassigned to immediate maintenance demands. Then, the automation encounters a condition outside its design assumptions. The human operator is asked to take control of a process no living person has ever controlled directly. Ritualization follows. A procedure survives because it is treated as sacred. Operators know that violating it once caused a dangerous event, but the explanation has been shortened with each retelling. Eventually, the steps remain while the causal model disappears. Step 7 must come before Step 8, because that is how it has always been done. If hardware changes during a repair, the old sequence may no longer be correct, yet no one possesses enough understanding to revise it safely. A single expert bottleneck makes the danger immediate. Only one person fully understands reactor neutron monitoring. Only one can rebuild a biological sensor. Only one remembers why a modified water valve must never close during oxygen regeneration. When that person dies, the ship does not lose stored files. It loses the ability to interpret them. Education should prevent this. But education also drifts. The curriculum was written for the original ship. After 2 centuries, systems have been replaced, rerouted, and modified. Teachers continue using old simulations because new ones were never completed. Students learn about equipment that no longer exists while receiving only informal instruction on the equipment that actually keeps them alive. This is curriculum drift. Language changes as well. Pronunciation shifts. Meanings move. Technical abbreviations acquire new interpretations. A warning written 300 years earlier may still be readable, but one critical word may no longer mean exactly what its author intended. Then the archive itself begins to decay. Storage media accumulates errors. File formats become obsolete. Indexes are corrupted. Several copies may survive, but if all descend from the same damaged master, redundancy preserves the corruption. Without an external reference, the crew may not know which version is authentic. Knowledge preservation must therefore be active. Simulators should recreate rare failures before those failures occur. Operators must experience conflicting sensors, incomplete shutdowns, and unexpected interactions between systems. Apprenticeship must extend across generations. Every expert needs more than one successor, and every successor needs supervised contact with real equipment. Rotational cross-training prevents knowledge from becoming trapped inside one profession. A physician should understand basic water chemistry. A reactor engineer should know emergency medicine. A biologist should be able to operate the machine shop. Periodic certification must test performance, not memorization. The ship must preserve design rationale as carefully as operating instructions. A manual should explain not only which valve opens first, but what pressure transient the sequence prevents. Records should exist in multiple formats. Advanced digital archives can hold enormous detail. Simpler media provide a path back if complex readers fail. Essential documents must remain accessible with tools the ship can reproduce. Black Start manuals become especially important. They explain how to rebuild essential capability after widespread power loss. They begin with the smallest surviving energy source, then restore control electronics, cooling, atmosphere, water, and finally, the larger power system. They are instructions for waking a nearly dead civilization. Even if all of this succeeds, the mission faces a second shock. Another ship may leave Earth later and arrive first. This possibility is sometimes explored through the logic of weight calculations. If propulsion improves quickly enough, delaying departure can allow a later spacecraft to overtake an earlier one. It is not a universal law. Technological progress is irregular. A breakthrough may never occur. Political collapse may stop further launches entirely. But the possibility is enough to wound the mission. The first generation accepted hardship to become pioneers. Their descendants may receive a message announcing that a faster vessel has launched. Years later, another message may report that it has passed them. The newer ship may reach the destination, while the older vessel is still decades away. The mission is no longer first. Its technology is obsolete. Its survey objectives have already been completed. Its descendants are suffering for an achievement another crew accomplished with less sacrifice. Or Earth may simply become silent. The silence could mean transmitter failure. It could mean that Earth lost interest. It could mean technological regression, war, or extinction. The crew cannot know. Purpose is not listed on an engineering diagram, but it supports every system. People maintain machinery because they believe tomorrow is worth protecting. When that belief disappears, preventive maintenance is postponed. Education feels pointless. Cooperation weakens. Old political conflicts gain new force. The ship may survive radiation, starvation, and mechanical decay. It can still die when enough people stop believing that survival has meaning. Then the destination star appears. Every generation has lived and died for this approach. One system has remained dormant through much of the voyage. Now it must awaken and perform the most precise engine burn in human history. The reactor is still operating. The farm remains green. The water is safe. The population is stable. The destination star now dominates the forward instruments. The deceleration engine receives its startup command. A valve moves. Then it stops before reaching the fully open position. After 400 years of surviving radiation, disease, political conflict, and mechanical failure, the ship has minutes to prove that the entire voyage was not a mistake. This is the dormancy paradox. The propulsion system must work at departure. It must accelerate the ship toward interstellar velocity without destroying the structure or crew. Then, much of it may remain quiet for decades or centuries. At arrival, it must restart. It must produce sufficient thrust in the correct direction for the required duration. There may be no second attempt if the propellant reserve is limited, or if the ship passes the critical point in its approach trajectory. Dormancy is not preservation. A seal can become brittle, even when no fluid moves through it. Polymers lose plasticizers. Radiation breaks molecular chains or creates new crosslinks. Temperature cycles change dimensions and stress interfaces. When pressure returns, The seal may crack. Lubricant can migrate away from a bearing surface. Liquid components evaporate or separate. A bearing that remained under load in one position can develop brinelling, leaving permanent depressions in its race. When rotation begins, those depressions generate vibration. Valve stiction can prevent movement after long inactivity. Surface films, corrosion products, or degraded lubricant make contacting parts resist their first motion. The actuator may still operate. Its force simply may not be enough. Propellant lines introduce further risks. Residual material can react slowly with internal surfaces. Contaminants may form deposits. Dissolved compounds can precipitate or crystallize near narrow passages. An injector does not need to become fully blocked. Uneven flow can create unstable combustion, hotspots, or destructive pressure oscillations. Electrical contacts corrode at microscopic interfaces. Insulation becomes less reliable. Pyrotechnic igniters and other energetic materials change as chemical components age. Sensors drift. A pressure transducer may support that a chamber is stable when actual pressure is climbing. A flow meter may underreport propellant delivery. The control system can command the correct response to the wrong measurement. Cryogenic propellants create a separate storage challenge. Liquids such as hydrogen must remain at extremely low temperatures. Heat leaking through insulation causes evaporation, known as boil-off. Active cooling can reduce losses, but refrigerators require energy and machinery throughout the voyage. Hydrogen molecules are small and difficult to contain. Materials can also experience hydrogen-related degradation depending on alloy and operating conditions. A design that depends on storing cryogenic propellant for centuries must demonstrate more than a well-insulated tank. It must maintain an entire thermal control and containment system for the same duration. The deeper problem is energy. Reaching interstellar velocity is only half of the journey's velocity change. The ship must remove that velocity at the destination. A vessel that cannot slow down does not arrive in the useful sense. It performs a flyby. At 10% of light speed, a star system can pass from distant target to receding object in a very short period compared with the centuries spent reaching it. Instruments may collect extraordinary data, but the crew cannot settle, enter orbit, or turn around. Several braking concepts have been proposed. A magnetic sail would use a large magnetic field to interact with charged particles in the interstellar medium or the destination star's stellar wind. The resulting drag could reduce velocity without consuming conventional propellant. An electric sail would use long-charged tethers to interact with moving plasma. Antimatter-assisted concepts attempt to exploit the enormous energy density of matter-antimatter reactions. These ideas remain research concepts. None has been demonstrated as a complete braking system for a crewed interstellar vessel. The density of the surrounding plasma varies. Large magnetic structures face mass, deployment, and reliability challenges. Antimatter is extraordinarily difficult to produce, store, and handle in meaningful quantities. The braking system must also control direction. Thrust must pass close to the ship's center of mass. If it does not, the vessel begins to rotate. Control systems must correct the torque while maintaining the intended trajectory. The center of mass will not be exactly where the original designers predicted. 4 centuries of consumed supplies, relocated water, replaced shielding, and rebuilt machinery have changed it. A small thrust vector error, sustained during high-speed approach, can produce a large navigational miss. The ship may pass the wrong side of a planet, or fail to enter the region where later maneuvers remain possible. The partially open valve limits propellant flow. The engine ignites, but chamber pressure remains below target. Thrust rises, then stabilizes at an insufficient level. The crew faces an impossible decision. Continuing the burn consumes the remaining propellant without guaranteeing capture. Shutting down preserves fuel, but leaves the ship moving too fast. Engineers modify the control limits. They accept higher temperatures. Pumps are pushed beyond their certified operating range. The thrust increases. It is still not enough. The destination system expands across the instruments. Planets that were once unresolved homeward changes in starlight become worlds with clouds, mountains, ice, and shadow. The sensors that survived for centuries finally see them at close range. Then the worlds begin to recede. The ship has not lost all velocity. It cannot enter orbit. It passes through the system and returns to interstellar darkness. There is no fuel to reverse course. No second destination has been prepared. There is no path home. This ending does not prove that interstellar travel is impossible. It proves that a responsible civilization cannot allow its first full test to carry human lives. The path must begin with closed biological loops tested on Earth for longer and longer periods. It must continue through autonomous habitats in orbit and on the Moon. Mars missions can test delayed communication, onboard medicine, local manufacturing and repairs performed without immediate rescue. Robotic scouts must reach an interstellar destination before settlers. They must examine atmospheres, radiation, resources, dust conditions, and orbital hazards. Uncrewed vehicles must demonstrate acceleration and deceleration. Life support systems must prove that they can be repaired from onboard resources. Factories must reproduce their own critical components. Archives must survive hardware changes without losing meaning. Only then can a crewed vessel claim that its survival is based on evidence rather than hope. A real starship is not defined by maximum velocity. It is defined by water that remains clean after billions of passages through the recovery system. By a child who still understands the reactor built by distant ancestors. By a community that protects human dignity when every liter of water and every calorie is limited. And by an engine that starts after its designers have been dead for centuries. The stars do not require humanity to hurry. The real challenge is not building something capable of touching them. It is becoming a civilization patient enough, honest enough, and responsible enough to arrive without sacrificing the very thing it intended to carry.